Hi, I'm Ryan Newman, and for as long as I can remember, I've been racing cars. My family and I spent nearly every weekend of my childhood at different racetracks while I chased my dream. But that was not the greatest gift they gave me. My parents insisted that I go to college. The science, math, engineering, and technology I learned in college continue to make me a better driver. What most people don't realize is that stock car racing is not a one-person sport. It takes an enormous team of talented engineers, scientists, and mechanics to design a total plan for success. In this episode of NASA Connect, NASA engineers working to provide power to the International Space Station and stock car racing engineers designing powerful engines for competition help you learn how they use data to make important design decisions. And students from Phelps, Kentucky will show you how to build a simple vehicle, collect data, and refine your design based on observation and data collection. All on this episode of NASA Connect, TeamExtreme, Statistics of Success.
I wonder which of these engines would be best for a race car. Should I choose the one that is the biggest? Or maybe the one that looks the coolest? Or, I wonder how they make these decisions.
Oh, hello everyone. Have you ever wondered how extreme machines are designed and built?
Whether it is something as complex as a space shuttle or as powerful as a race car, teams of specialized researchers, engineers, and technicians work together to design, build, test, and redesign these modern marvels.
When designing an extreme machine for a winning mission, such as a stock car for a national competition, researchers work within a set of rules and regulations.
It's often the driver of a race car who gets all the attention, but much of the sport is about applying technology to a given set of rules to make the best vehicle. The rules describe how to build the car, but it is the engineers and technicians who make the car better, safer, and faster. It is the testing, measuring, and analyzing of data engineers do to help them make decisions refining the design of the car.
As you watch today's show, I will ask you several challenge questions that are designed to get you thinking critically and discussing the topic.
Teachers, you'll want to pause the program and have students work in small groups or write in their science journals as they think about these questions.
Here are my first questions to get your brains revved up.
In your own words, define work, energy, and power.
How do you think work, energy, and power are related?
Teachers, now it's a great time to break from the program and work on these questions. Hello everyone, how did you do? The work that I asked you to think about is work in the physics sense, not homework or a job.
In physics, work is simply the applied force multiplied by the distance, with one catch. The distance only counts if it is in the direction of the force you apply. When you do work, you use energy. Energy is the capacity to do work. There are different types of energy, such as potential energy, kinetic energy, heat, electrical, and chemical energy. Energy cannot be created or destroyed, but only change from one form to another. Each time when work is done, energy is involved. Think about the space shuttle. It is one of the most complex machines ever designed and built, and it uses energy to do work.
Have you figured out the relationship between work and energy? The unit of measure used for both work and energy is the joule. In the case of the space shuttle, chemical energy is transformed into work, which is transformed into kinetic energy.
In order to launch the space shuttle from the launch pad, its engines have to apply enough force to counter the force of gravity, pulling on its mass and aerodynamic drag on the body. It does work as it applies this force over a distance. The work of the shuttle's 3 main engines and 2 solid rocket boosters is to lift the shuttle into orbit. As a matter of fact, it only takes 8.5 minutes for the shuttle to go from 0 to 17,500 miles per hour. People often confuse energy and power, so let's figure out exactly what power is. Power is the rate at which work gets done or energy changes. You need more power to run up the stairs than you do to walk. Same amount of work, shorter time to get it done. If you want to get the same amount of work done in a shorter amount of time, then you need more power.
Are you still thinking about the relationship between energy and power? The unit of measure for work and energy is the joule, and the unit of measure for power is the joules per second, or the watt. For example, a 100-watt light bulb requires 100 joules of energy per second to keep it lit. Let's investigate further.
The space shuttle's main engines are critical to a successful mission. They have been carefully engineered to produce huge amounts of power during launch. Without that enormous power, the rate of doing work would be too slow and there wouldn't be enough force to overcome gravity and drag. If you're an engineer designing a rocket, you need to know the difference between energy and power. The 3 space shuttle main engines generate the maximum equivalent of about 37 million horsepower.
Do you know how many 100-watt light bulbs you could light with that amount of power?
The engines in today's race cars produce upwards of 850 horsepower, but they did not always make that much power. How do you think they were able to design and build these engines to generate all that power? Let's visit the Penske racing team in Mooresville, North Carolina to help us figure this out.
Hi, welcome to Penske Jasper Engines. This department is responsible for all the racing engines for Penske Racing South. Our job is to try to run an entire season at top performance without an engine failure, an astronomical task. We start off by choosing the internal parts of our engines very carefully. We study the materials and quality of the workmanship of the parts very closely. Here in the shop, we have very strict rules and procedures for machining each part of the engine. We have guidelines within the shop for assembly and machining procedures. We also have a sophisticated testing program here in the shop to determine weaknesses in the engine before we get to the racetrack. Our mechanics and engineers carefully collect huge data sets about every piece in the engine as they test it. Sometimes we are looking for the average performance of a part. Sometimes, however, we are looking for the highest number in a data set, and still other times we are looking for the lowest number in a data set. These are called the maximum and the minimum values. It really all depends on the design decision we need to make.
Hi, welcome to Penske Racing's engine test facility. One of the tests we perform uses one of these, an engine dynamometer. If you want to know the horsepower of an engine, you hook it up to one of these machines. A dyno places a load, or force, for the engine to work against and measures the amount of power that the engine can produce against that load. You can get an idea of how a dynamometer works in the following way. Imagine that you turn on a car engine, put it in neutral, and floor it. Eventually, the engine would run so fast it would explode. That's no good. So on a dyno, you apply a load to the floored engine and measure the maximum load the engine can handle at different engine speeds. We take the data from the dynamometer and plot it on a graph to look for the engine's maximum horsepower. This is an important data point to know because that is where we want our driver to operate the engine for peak speed during a race.
Different races have different rules that determine which engine each team can use. An engine is an air pump. If you restrict the amount of air that the engine can take in, you simultaneously restrict the horsepower the engine can produce. A restrictor plate engine has a metal plate with 4 holes in it. This plate is set under the carburetor to restrict the flow of oxygen into the engine. This limited airflow limits the level of combustion and limits the power the engine can produce. These restrictor plate engines make an average of 450 horsepower. The open engine, on the other hand, has nothing to limit the airflow into the carburetor. These engines will, on average, make about 850 horsepower, an extreme increase over the restrictor plate style.
Here at Penske Racing, our engineers are in the business of designing and building high-performance cars. A car is considered to be high performance if its horsepower is very high compared to its total weight. This makes sense. The less weight you have, the less force and power is required to get the same amount of work done. For a set amount of power, you want as little weight as possible to maximize the work getting done. If you want a fast car, you want a good power-to-weight ratio. You want lots of power and minimal weight. So the first place to start, Ryan, is by cleaning out your trunk.
Huh? Those are some really sweet rides, but did you notice what they were using to tweak those powerful engines? Their data. That's right, they were using the power of math to create a more powerful engine. We heard them use words like maximum, minimum, data set, and average. Let's take a closer look at what some of these words mean, and a couple others just for kicks.
When you collect data, you can end up with a lot of numbers, but how can you use them? A good rule of thumb anytime you are going to be working with a set of data is to put it in rank order from lowest value to highest, like this. The highest value in the set is the maximum, and the lowest value in the set is the minimum.
Rank order is a great way to use statistical analysis with your data. Statistics allow us to look at numbers from different points of view. Remember the dynamometer? The car engineers use a range of numbers to help them design the most efficient car for a specific track. To learn more about these different kinds of racetracks, visit www.nascar.com or www.penskeracing.com. Another way to look at numbers is to find the mean, median, and mode. Each one is a different way to describe the center point of data, and each can be used for different purposes.
The mean is what is generally referred to as the average. A dictionary definition would be equally far from two extremes. You calculate the mean by adding together all the values you are given and dividing the sum by the number of values.
Try this example.
Find the mean mass of 6 friends. Their masses are as follows: 57.6 kilograms, 60.3, 65.9, 75.8, 58.9, and 48.1 kilograms.
Teachers, now might be a good time to take a break and let students try finding the mean of the dataset themselves. Remember, working with a partner can be a good way to try something new.
Welcome back. How did it go? Let's compare your work with mine.
Adding those masses together gives a sum of 366.6. Divide the sum 366.6 by 6, the number of values, and you are left with a mean or average mass of 61.1 kilograms.
Okay, let's take a look at the next one.
The median is a number that's situated in the middle, and it's calculated quite differently from the mean. To find it, you simply put your data in rank order, and it is literally the number exactly in the middle. Now, what happens if you have an even number of data points in your set? Well, you take the two in the middle and find their mean. Let's see if you can find the median in the following example. 6 friends go shopping, and they spend the following amounts of money: $15, $24.50, $3.75, $43.99, $28.10, and $17.68.
Teachers, let's take a break from the show so the students and I can work on this. Oh, how did you do? Did you remember the first rule of thumb when working with the data set? Sure, put it in rank order.
In this case, the order is $3.75, $15, $17.68, $24.50, $28.10, and $43.99. If there is an odd number of values, consider the middle value the median. Since there are an even number in this example, the median is the mean of the two middle values. Those values are $17.68 and $24.50, and the mean of those two is $21.09. Therefore, the median amount is $21.09. If your data set has outliers, that is extreme values at either end, then the median may better represent the center of the data set.
So how did you do? Great! So let's check out that third term, mode.
The mode is the value that appears in a set of data most frequently. Check out what I mean. Look at the ages of these 6 friends. There are 3 who are 14, 1 who is 15, and 2 who are 16. What should be the mode for this set of data?
Hey, how did you do? Here's what I found.
The most frequent value is 14. Therefore, 14 is the mode. This method could be used by a company trying to target the largest market for its product.
The nice thing about using numbers is you can use and interpret them in different ways. Once you realize that, you may be able to put them to use. Now that we all have a better idea of some ways to look at a data set, let's visit students from NASA Explorer Schools in Phelps, Kentucky.
Our class worked in groups to design, test, and redesign vehicles. They were easy to make, and we had a lot of fun testing them and refining our designs. First, each group received 3 each of the following: spools, paper clips, washers, and popsicle sticks. Each team had to select 3 rubber bands they thought would make its car travel the farthest. Next, we built our vehicles. Teachers referred to the lesson guide for instructions. For the first test, we chose a rubber band and slipped it through the spool like this. We attached one end of the rubber band to the paper clip and then attached the clip to the spool with tape. Over the other end of the rubber band, we slipped a washer and then put our popsicle stick through the rubber band like this. Now we revved up our engines by twisting the popsicle stick. The rubber band begins to store potential energy as you twist it with the stick. Then we put the vehicles on the starting line and let them go. They began to roll as the rubber band unwound. The potential energy stored in the twisted rubber band was converted to kinetic energy. Because we were going to test more than one rubber band, and we wanted to test only one variable at a time, we made sure to use the same number of twists for each trial run. The next variable that the groups explored was the number of twists we put into our chosen rubber bands. The groups then worked to analyze their data, just like engineers, finding the mean, median, and mode for each test. It definitely made us realize that engineers don't just guess when they create a design for a vehicle or make modifications to that design.
They use the data to help make the decisions.
Come on.
There you go.
If we're going to beat these guys, we're going to need a bigger rubber band.
10-4 on that.
Wow, that looked like a lot of fun. It looks like the Penske team had fun with this too. You know, just like the Penske racing team members and the students you've seen so far, NASA has its own extreme team that works to provide power to one of the most radical rides of all. Imagine a machine that you and your friends could use to travel around the world in 90 minutes.
Now imagine that this machine had its own kitchen, bathroom, gym, sleeping quarters, and several laboratories. That would be a really extreme machine.
Guess what? This machine really exists.
It is the International Space Station. Being built by a team of 16 nations, when this machine is complete, the International Space Station will have a mass of about 453.6 metric tons. It will measure 108.5 meters across and 88.4 meters long and will be home to 6 state-of-the-art laboratories.
How do you think this incredible invention gets enough power to operate? How do you think we are able to design and build a system here on Earth that can provide enough power for us to work out there in space?
For some answers to these questions, let's visit with engineers and scientists from Pratt & Whitney Rocketdyne in Canoga Park, California. This group helped NASA design the elaborate power systems for the space station.
Hi Ed, thanks for having me.
Hi Derek, glad you could make it.
I was hoping you can help me understand how the system for providing power to the International Space Station was designed.
Sure, be glad to help. Come on. If you're going to do long-term research in space, you have to have a readily available source of energy that is reliable and easy to harness. That's why we designed a power generation system that uses the energy of the sun. The method we use for harnessing the sun's energy is called photovoltaics. The word photovoltaic is made from 2 smaller words, photo, from the Greek word meaning light, and voltaic, from the name of Alessandro Volta, a physicist who in 1800 arranged zinc and copper disks in a column, creating the first storage battery. So today we use the term volt to describe how much electrical potential is present in something like a circuit or a battery. Photovoltaics can be made from several different materials, but most commonly use purified silicon cells to directly convert sunlight to electricity.
Dr. Golston, is this method similar to what makes the solar calculator work?
Yes, indeed. The solar cells on this calculator are very similar to the ones on the space station. Photovoltaic arrays are simply a group of cells electrically connected and packaged in one frame. Once used almost exclusively in space, photovoltaics are now used more and more in less exotic ways, like parking lot signs, emergency roadside phones, backyard lights, even toys. They could actually be mounted on your roof and help power your house. For the space station, one of the first design challenges engineers faced was figuring out exactly how large the solar panels needed to be to generate enough usable power for the station. Now, the concept of power is important. It's not enough to know about energy alone. You have to also specify the rate at which you deliver that energy. So on the space station, if we don't deliver the energy fast enough, in other words, at a high enough power, then the space station won't be able to do its job. What the data showed us was that solar cells produce different amounts of power as time goes on. When they're new, they're able to produce much more power. As they age, the material they're made from begins to slowly deteriorate, reducing the amount of power generated. We had to determine the average amount of usable power the completed station would need and design a system that, as it aged over 10 to 15 years, would continue to provide the right amount of power.
That's an amazing amount of planning. Okay, kids, let's figure out how solar cells work.
Basically, when light strikes a solar ray cell, a certain portion is absorbed by the semiconductor material, and the energy of the absorbed light is transferred to the semiconductor. The energy knocks electrons loose, allowing them to flow freely. This flow of electrons is called current, and by placing metal contacts on the top and bottom of the photovoltaic cell, we can draw that current off to use externally. This current can power your calculator, a garden light, or even something as large as a space station. The 8 solar rays on the ISS are large, flexible, deployable mechanisms that resemble wings. However, they have nothing to do with flight. These arrays will produce, on average, 144 kilowatts of power, which is enough to run 60 average-sized homes. Each solar ray is about 72.5 meters long and is connected to the space station's 94.5-meter-long truss and extended outward at right angles to it. Altogether, they will cover an area of 1,902.3 square meters, or about an acre. An array consists of 2 solar array blankets, one on either side of a telescoping mast that extends and retracts to form or fold the array wing.
Wait a minute. Why do they have to extend and retract?
Well, Derek, that was another design challenge we had to face. We knew from our data that the cells would have to be big, really big, enough to generate enough usable power for work on space station. Because the only way these solar rays would travel to the space station would be aboard NASA's delivery truck, the Space Shuttle.
Oh, I get it. Because the shuttle's cargo bay is only 18.3 meters by 4.6 meters, that means everything delivered to the space station, including the actual parts to build it, have been designed in sections that fit into this space.
That's right, Derek. In this case, the huge solar arrays were designed to be folded like an accordion so that they would fit into this space. Prior to installation, solar arrays are packaged and stored at the Kennedy Space Center in the payload processing facility. Once in space and installed on the station, the accordion-folded arrays are extended just like someone unfolding a paper fan. When fully extended, a pair of solar arrays spans about 73.17 meters, the largest deployable space structures ever built.
Morale, Eric showed me some very powerful solar cells. But you know what? I've been wondering something.
What's that, Derek?
These are solar arrays, so that means they must rely on the sun's energy to generate power. I know that the space station orbits the Earth about every 90 minutes. Its time in the sun can be as short as 35 minutes and as long as 55 minutes.
This gives us a range of 20 minutes. The difference between 55 minutes and 35 minutes, and a mean or average exposure to the sun of about 45 minutes. Do you remember how we find the mean? I added the two numbers together and divided the sum or total by 2. My mean is 45 minutes.
So how does the station get enough power to operate when it's in the Earth's shadow?
Great question, Derek. One solution to this problem was to design the solar arrays so that they turn on gimbals to keep them facing the sun for as long as possible. Another solution to this problem is to store energy in batteries for later use.
Wow, that is some powerful engineering. Now that I understand how the solar array collects energy from the sun, how do you take that energy and convert it back into useful electricity?
Well, in order to create useful energy, the space station relies on its power modules. The power modules contain 3 important systems. First, the power generation system. This consists of the solar arrays, which we have already talked about. Second, an energy storage system made of the largest set of batteries ever flown in space. And finally, a distribution system, which is similar to the fuse boxes, wires and switches that allow electricity to move safely around your house. Part of the power generated from the solar arrays is used to charge the space station's battery stations, called the energy storage subsystem. The batteries are used when the space station is not in sunlight. The batteries are also used to boost power levels on the space station when more is needed for experiments and research. Power generated by the solar arrays, not used to charge the batteries, goes directly to the laboratories and modules of the space station. This power also runs the life support systems, which includes the air the astronauts will breathe, the food systems, and the environmental systems, to name a few. As the space station grows, more people will live and more research will be done on the space station. The average amount of power needed will go up, engineers have anticipated this by studying current power usage and predicting future power needs. They have designed the power system to grow along with the station so that all the important work NASA has planned gets accomplished.
Thank you so much, Morale, for helping me understand how the space station electric power system is designed.
My pleasure, Derek.
You know, living and working in space is an exciting adventure. Even the way the International Space Station will receive its electricity is wondrous.
Electrical power is the most critical resource for the International Space Station because everything on the station depends on it. Electricity allows the crew to live comfortably, to safely operate the station, and to perform scientific experiments.
Worldwide research in chemistry, biology, physics, and other sciences is conducted in the space station laboratories.
This research is opening the door to future long-duration human exploration of the solar system, as well as providing continuous benefits to science, industry, and medicine on Earth.
The benefits of space research appear as innovative commercial products that improve our lives each and every day. Whether you are determining the maximum horsepower for an extreme race car or finding the maximum power output for the International Space Station, you can use statistics to ensure your success.
Well, that wraps up another episode of NASA Connect. We'd like to thank everyone who helped make this program possible. So until next time, stay connected to math, science, technology, and NASA. We'll see you next time.